But you will want to get the meaning of the word, ionization energy, because it seems to show up a lot as far as the... Today we will want to focus on the trends in the periodic table, why certain trends occur, and those properties that we want to discuss are the ionization energy, electronegativity, electron affinity, and what's the ionic radius have to do with it? It seems like too many variables to think about. And of course, we got to think of the size of the atom itself, because I should probably make this a different color. And I probably should do a quick sketch and see if I can successfully draw a covalent bonded atom. If I have covalent, this would be the plus, and then this would be the minus. And then for the metals, and then metallic, it's done in 90 minutes, because that's all the film space they have, or time as far as the videotape. There are so many activities going on here at Broward College, and so we'll try to get chapter 8. So our lecture for tonight talks about periodic properties of elements. So we want to ask the question, why do atoms behave in a certain way? And we can we can actually predict their behavior based on where they appear in the periodic table. So how do ions move across cell membranes is a really good application. You will note that for those of you that are taking biology, which one is inside the cell membrane and which one is outside? Who would like to, who knows that? Sodium is outside, potassium is inside. Very good. Okay, but can you believe that our cell membrane can actually differentiate between the two pumps? And why? Because of the radius. The radius of sodium and the radius of potassium are quite different. And so the trend as you go down the group, right? So you see group 1. So you have lithium, sodium, potassium, rubidium, cesium, and then francium. So you have sodium and potassium. So like Latoya said, sodium is inside or
No,
outside?
sodium is outside.
Outside, and potassium is inside. And I'll post. There's actually a good simulation on how that goes, because the channels actually, when it needs sodium, so it will conform itself into a particular shape, or when it needs potassium, or if there's too much potassium, it will form in a different shape, and potassium ions will get out of the internal inside the cell membrane. So sodium ions are pumped across membranes, and because of their size, that their behavior can actually be predicted. And we learned that it was actually Dmitry Mendeleev that developed the periodic law, where he ordered the elements by atomic mass, and he saw a repeating pattern. And so as a result, he arranged elements in the order of increasing atomic mass. And so this is what he came out first, some examples of some elements that he got. For example, gallium. He called it aluminum, just like aluminum. Very similar properties, because if you look at gallium, it's right underneath aluminum. And you also see germanium, right? So he called it silicon because it has similar properties of silicon. So he predicted these properties, where germanium's atomic mass unit should be around 72, and the actual measurement was 72.64. Isn't that really quite interesting? And the density, 5.55, and the actual was 5.35. And the formula for the oxide, so we got GeO2, and for the chloride, GeCl4. So, and similarly for gallium. So that was really quite a remarkable feat. So this law predicts what the properties would be, but it does not really explain why the properties exist in that fashion. We learned in chapter 7, right, through the quantum mechanical theory of the atom, why the periodic trends do exist. And we come up with electron configurations, and we have successfully calculated the solution to Schrodinger's equation for hydrogen, but for multi-electron atoms we actually can't. But we should ask our question, how do electrons occupy the orbitals? We learned about, Schrodinger's equation, that one electron will always first occupy the lowest energy orbital, which would be the 1s. And that for the multi-electrons, we cannot actually solve the Schrodinger's equation because of all the interactions going on, attractive and repulsive forces going on, and all the shielding and penetration that we'll be learning today. But two concepts that we want to at least focus on today is the electron spin, whether it will be spin up or spin down, and how energy levels can be split into different degenerate sublevels. So it was Stern and Gerlach that found that silver atoms can be split in two by a magnetic field. And that when these electrons spin, they actually generate a magnetic field. Where one points north and the other one points to the south. So spin is a fundamental property of their electrons, and we refer to their orientation as either spin up, arrow up, or arrow down. And this is what our M sub s that we learned in chapter 7. We refer to that as a spin quantum number, M sub s, because there's a postulate that no electron can have the same quantum numbers, right, for the N, L, M sub L, and M sub s. So we'll see that shortly also. So the spin quantum number has a designation of M sub s. So for hydrogen, in this particular box orbital would be spin up. So we use like a single arrow, a single hook, right? By convention, a half arrow pointing up. So we have Pauli, who stated an exclusion principle where no two electrons can have the same four sets of quantum numbers, which we learned last time. And this quantum numbers, thank you. Knowing the number of orbitals in a sub-level, so we learned that the s is a one orbital. So if it's just one orbital, so it can only have two electrons. The p, we learned the x, y, and z, so it can have 6 electrons. We learned about their shapes also last time. The d sub-level has 5 orbitals, and the f sub-level has 7 orbitals. So if we take a look at helium, how many electrons does helium have? 2 electrons, right? And both electrons will be in the first energy level in the s orbital, but therefore it will have 2 spins, right? Spin up and spin down. 2 opposite spins. Did we get that? Okay. And then we can characterize it. So last, when we were talking about these different n refers to the principal quantum number by definition last time, right? And L, we said, was the angular. And M sub L is the magnetic, M sub s is the spin quantum number. And so no two, each atom, like for example for helium, these 2 electrons has different quantum numbers, right? That's by virtue of the spin up and spin down. Even if the N, L, and M are 1, 0, 0, but the spin up and spin down. So when the sublevel splits and you have a multi-electron, we call them, when they're in the same level, we call them it's degenerate, just like the px, py, pz, right? And there's also some charge interaction, shielding, and perhaps a third one called penetration also of a charge. And so the lower value of the L quantum number, the less energy the sublevel would have. So S would be less than P, which would be less than D, which would be less than F. And for those that are in engineering and know a little bit about electronics, we have Coulomb's law where the potential energy, E, right, of the atom is characterized by the charges that the atom has as well as the radius of Q1, the product of Q1 charge multiplied by Q2 over the radius times some fudge factor 1 over 4 pi epsilon sub naught. And for like charges, the potential energy is positive and decreases as it gets farther apart. But for opposite charges, it becomes more negative as it gets closer. So when you take a look at calcium, it has a 2+ charge. The electrons are more strongly attracted to a 2+ charge than for a nucleus with a 1+ charge. Okay, so you'll want to remember that. And then we go to the concept of effective nuclear charge and shielding as a result of the electrons, multi-electrons in an atom. So each electron in a multi-electron atom feels an attraction to the nucleus, but also a repulsion to the other electrons. So you get a net reduced attraction, and so therefore, since you have lots of electrons, then the outermost electrons are shielded from the nucleus, and you end up with an effective nuclear charge for the electron. And so here is a schematic of shielding and of experiencing the penetration of charges. And if we take a look at the 2p orbitals, right? You see how the s orbital really penetrates all the way down to the nucleus, right? So the 1s, but then the 2p doesn't penetrate the nucleus as much as the 2s. So it has a weaker penetration, so therefore those electrons are more shielded from the attractive force of the nucleus. And in the 4th and 5th principal levels, of course, then the s orbital, so this is a very important concept, lies lower than the d orbitals because of shielding and penetration. And if we take a look at, theoretically it should be when you write down 1s, 2s, 3s, 4s, 5s, you will note that the 4s is in fact slightly lower than the 3d because of its penetration. So not by much. So how do we go about filling the electrons in the sp, d, and f orbitals? We use the Aufbau principle, and take note that Pauli's exclusion principle tells us that no more than 2 electrons per orbital. And when we fill the orbitals, we have to make sure that we put 1 electron, so Hund's rule, 1 electron is filled in the degenerate orbital. So we can start, for example, if we look at krypton, Kr, and 36 electrons, right? Do you see that? So we can start writing 1s2, right? 2s2, 2p6, 3s2, all the way down to 3d10, 4p6. So a shorthand way of doing it would be to, if we wanted to do the same for rubidium that has 37 electrons, we just put a bracket and use the noble gas krypton, so Kr, that tells us that there are 36 electrons, and then we move on to the 5s1, because Rb, right, the previous noble gas was krypton. So that's how we would fill up atoms in their ground state. And this is how Aufbau way of filling electrons in the sp, d, and f. So probably if you have the PowerPoints, you have to draw or in your notebook, write down 1s, 2s, 3s, 4s, 5s, 6s, 7s, right? And then slowly go through, and then with your pencil or pen, right through this way. And so when we go, so the next arrow goes through the diagonals. So see if you can repeat that in your notebook or notes. And if we take a look at lithium, how would you go about doing lithium, right? So 1s, 2s, 1. So here's lithium. So 1s, so there's 2 electrons, right? And then we draw it all the way, and then 2s1. And so there's 1s, 2s1. So for beryllium, there are 4. So we continue 1s, then 2s2, right? Then we're getting ready to go to, what would be our next one? For boron, there are 5. So 1s2, 2s2, 2p1. And then, of course, carbon, 1s2, 2s2, 2p1. So this is really 2px1, right? 2py1. So the Hund's rule states that for degenerate orbitals, we need to fill them up one at a time. Okay? So we refer to valence electrons as electrons in the sublevel with the highest principal energy level, and which is also in the outermost shell. Electrons in the lower energy shells are referred to as the quark electrons. So when we write down the electron configuration for rubidium, so we write down the bracket, the noble gas before it, so krypton, 5s1. And so for the 5s1 electron in rubidium, so that quantum number would be n equals 5, right? It's the same 1, 2, 3, 4, 5, right? Starting with lithium, 1, 2, 3, no. Starting with hydrogen, 1, 2, 3, 4, 5. So n equals 5. L would be 0, m sub L is 0, and the spin would be plus 1/2. But for an electron in the sub 2p level, then n would be 2, L would be 1, m sub L minus 1. And we'll try to do some exercises also when we review for this. So the group number corresponds to the number of valence electrons. So we see group 1, group 2, and then you see group 3, group 4. The length of each block is the maximum number a sublevel can hold. The period, however, corresponds to the principal energy level of the valence electron. So rubidium is in group 5, right? You see the groups 1, 2, 3, 4, 5, and Rb is in 5. Okay? Good. And if you look at our periodic table,
is the group the number labeled
across
the top?
The group
right?
is the top, right? 1, 2, and then the period is the one across, right? So you see for Rb, rubidium is in group 5.
Or period 5.
And in period 5. That's correct. So if we take a look at our periodic table, here's rubidium in period 5, right? So period 1, period 2, period 3, period 4, but then this is group 1, right? Group 2, so these are the metals, the alkali metals. And of course, group 7A, they're the halogens. And of course, the 8A are the noble gases. So the outer electron configurations, and a new way of referring to them now is 1 through 18. But the old way when we learned this several decades ago, we would say group 1A, group 2A, group 3A, 4A, 5A, 6A, 7A, 8A. And when we look at the orbitals themselves also, you can actually see where the light blue ones are the S block elements, and the P block elements are the pink, and then the D block elements are the yellow, and then the F block elements are really light blue.
So you don't actually have to do that one.
Yeah, we'll do that. Yeah.
You have to, or you can just look at the table.
Oh, yeah, you can. Yeah, you can look at the table.
Look at the table and figure
Yes,
out which
yes,
are
exactly.
going.
Yeah. So we'll try to write down the electron configuration. We have some slides to work on that will show us. But this is another diagram of how the S, P, D block elements are located. So there are some irregular filling of the orbitals. We need to remember that the 4s is lower than the d, so we need to fill the 4s before the d. We just need to remember that. Okay? And so, for example, because there are some irregular electron configurations, and that what makes chemistry sometimes takes longer to report data, because we can predict there are theories that, periodic table, periodic properties will predict that chromium should have an electron configuration of the argon shell 4s2 3d4, but experimentally it's really argon 4s1 3d5. Why? Because the rule would be is that we need to fill the degenerate levels first, right? So we need to put an electron in each d orbital, even if it should be 4s2 3d4, because this is not as stable as this, potential energy-wise. Okay? And likewise with copper. Copper tends to be the argon shell, 4s1 3d10. And you know where are these elements located? Right? They're in the middle. So molybdenum also. The krypton shell 5s1 4d5. So d5 is what's found experimentally. Ruthenium 5s2 is really 5s1 4d7. And palladium is really 5s0 4d10 because it's more stable that way. So we have to make sure that our experimental data fits our theory, or the theory also aligns with the experimental data. So properties and electron configuration. So elements follow a particular periodic pattern, and elements in the same column, right, so the same group, will therefore have similar chemical and physical properties. And the quantum mechanical model of the atom in chapter 7 explains this. Because the number of valence electrons, because of the type of orbital they occupy, whether it's an sp or d orbital. We also learned then that noble gases have 8 valence electrons. And so it is a very, very stable and very, very unreactive or non-reactive because of the 8 or octet rule. However, if we take a look at the alkali metals, they have 1 more electron than the previous noble gas. So we learned in chapters 3 and 4 that they tend to lose an electron. And so when they lose an electron, they form a cation. While halogens, they have 1 electron less than a noble gas, so they tend to gain an electron. And and end up with a charge of -1. And so here's a rough sketch of, say, an ionic compound as opposed to a covalent compound. So this would be like hydrogen or oxygen gas, and then this would be like sodium chloride or potassium chloride. And then as we look at the electron configuration and ionic charge of metals and nonmetals. So metals and nonmetals form an ion. So when we form a group 1A forms with group 7, and group 2 forms with group 6A. So elements actually form ions with very predictable charges. So you see that in research? Just by looking at the periodic table, just like we said. You can infer for all these properties by just taking a look at the periodic table. Instead, actually most people, when asked what would be the most important thing you would like to take out of your book, if you had just to take one sheet of paper from a textbook, what would you choose? And what would you choose? The answer would be the periodic table, because it tells you of all the predicted behaviors and properties of the elements. So the electron configuration of ions in their ground state of an anion. So we take a look at sulfur, right? Sulfur S, which is 1s2, 2s2, 2p6, 3s2, 3p4. I highlighted the 3p4 because what does sulfur tend to do? It's in group 6, right? So it needs 2 more electrons. So it tends to gain the electrons. So what happens to it when it becomes a sulfide? So then the electron configuration becomes 3p6. Did we get that? Right? How many got that or how many did that? It's hard to picture, right? Gaining, but then it's a negative charge, right? Yes, yes, yes. What would be a good mnemonic or... We'll do more exercises and see how we can clarify that. So for magnesium atom itself, magnesium has an atomic number of 12, right? So 1s2, 2s2, 2p6, 3s2, but since it's in group 2, it tends to lose 2, right? So then it loses 2, so then it becomes 2p6. You got that, right? That's easy. That is the other one that's a little bit. Could have a misconception. So what is the trend in atomic radius? Remember, this is one of the questions you will need to know because you'll be assessed one of the learning outcomes. What's the trend in the atomic radius? So there are several methods of measuring the radius. So when you have a covalent bond like bromine, Br2, right? You can look at the covalent radius, or you can look at the van der Waals radius, as in krypton, where the van der Waals radius refers to the non-bonding radius, but the covalent radius has to do with the overlap, right? The bonding radius. So atomic radius is an average radius based on the numbers of the compound. What is the trend in atomic radius? What happens to the radius as you go from the top to the bottom of the group? It increases, and as you go from left to right, it increases. So make sure you know that, right? So if you have a periodic table, so you arrow up, arrow down as it increases the radius, right? And then as you go from left to right, what is it also? What did you say, Reed? What happens to the radius as you go from left to right?
thought it decreases the movement.
So atomic radius decreases across the period, but increases down the group, right? So decreases left to right. But as you keep on adding, but it's not true when it's the ions, so you'll know. So the atomic radii, here are the alkali metals, and here are the noble gases. So it increases, but then decreases, right? Going left to right. So more of the same. And we come to what we refer to as shielding. When you have several electrons and they're simultaneously attracted to the nucleus, outer electrons are shielded by the core electrons. And this screening or shielding effect causes a change in the nuclear charge. And so you come up with an effective nuclear charge, Z, where the effective nuclear charge is the nuclear charge and minus the number of electrons in the lower energy level, C minus S. And so screening and effective nuclear charges, so if you have a nucleus that has a 3+ with a valence electron of 2s1, so then there are 2 core electrons of 3+ minus 2, so the effective nuclear charge would be +1. But this doesn't tend to show up in our learning outcomes. It needs to be assessed, so I don't see questions like this also in the test bank. But that just gives you an idea that hence we are not really able to calculate and solve for the Schrodinger equation for multi-electron systems because of all these different types of attractive and repulsive forces going on, right? So for the quantum mechanical explanation, the size of an atom is related to the distance of the valence electrons from the nucleus, and the larger the orbital, the farther it will be from the nucleus and the less attraction. And so when we so this again reiterates the going down a group. The larger the principal energy level, the volume gets bigger, and so the quantum mechanics predicts the atom should get larger as we go down the column, which is in fact is true. And so the larger the effective nuclear charge, the more attraction the valence electrons have for the nucleus. And going across the period, what happens to the effective nuclear charge? It increases. So you will probably want to write down in a periodic table, Z effective increases going across the period. And then, what is the trend for the transition metals? The transition metals are pretty much the same size across the d orbital, and so their effective charge will be approximately the same. But this is where you'll need to know how to fill in the electron configurations for cations and anions, right? Not only should you be able to know how to fill up the configurations for the ground state of the atom itself, but also if it becomes an aluminum +3 cation, so instead of 3s2 3p1, now you have, since aluminum is 3+, so we need to get rid of the 3 electrons. And so then you have 1s2, 2s2, 2p6. or as you write down the helium shell, or core shell, right? Then 2s2, 2p6. So any questions there? Right? So you should see these type of questions in the next exam. Be able to write down, because it's in your one of your learning items, the electron configuration of atoms and cations and anions.
The next exam is going to consist of chapters.
So the next exam should cover chapters 8, 9, and 10.
Okay.
So what transition metals form cations? If we take a look at iron, because iron is such an important, physiologically important ion in our body, iron can form a 2+ or a 3+. So if it's a 2+, so here is the iron atom. So iron is in the 4, 2, 4. So you have 4s2, 3d6. So when it forms a cation, it can be in the form of 3d6, where you lose the 4s2 first, right? Because the d is lowered. Or it could be a 3d5, because that's actually very stable also. So iron that hemoglobin, right, is what charge do you think? +2 or +3?
+2.
1 + 2. +2. Double check that with your bio professor, see if it's in fact, and find out why. Or you can Google it now, right? And find the explanation. So Google is welcome in our class. So trends in the ionic radius. Ions in the same group have the same charge. Ion size also increases down the column. Cations are smaller than neutral atoms, right? So for example, if you had sodium and then you had chlorine, but then sodium lost an electron to chlorine, so it became sodium chloride. And so, see how much smaller the sodium atom? Even if sodium is smaller, it became even much smaller than the chloride anion. So you almost have to visualize covalent bonding, ionic bonding, right? And later on we'll go to metallic bonding also. But cations are smaller than neutral atoms. Cations are also smaller than anions. But of course there are exceptions to the rule, right? You have rubidium and cesium plus is bigger, or you have fluoride and oxide have similar sizes. But the trend, of course, group 1, and you see how the cations with respect to, so group 1A, group 2A, group 3A. Just like we said, as we go down from left to right, they decrease. So when atoms form cations, the valence electrons are removed, and so the cations got to be much smaller than the atom, right? And then when anions form, then they in turn get much larger than the atom itself. So group 6A and group 7A. And we have fluorine, fluoride, oxide. So fluoride and oxide, they can have the same size, right? Chloride, sulfide, bromide. And then trends in the anion radius, when atoms form anions, electrons are added to the valence shell. And we saw that. So traversing down the group, it causes the anions to get larger. And so going down the group, causing the anions to get larger. Going to the right across a period will decrease the effective nuclear charge, causing the anions to still get larger. So now we come to the term called ionization energy. What's our definition for ionization energy? Did anyone get a definition for that? What does our text say? Kayla, you have your textbook. What's the definition of ionization energy? We have one, Jeremy, or
Isn't it when it like loses one electron?
yes,
and then the
ionization
second
energy.
level
Yeah,
is two
yeah.
electrons?
Yeah, good. Yeah, you do know it. Cool. So the energy, ionization energy to remove an electron. So first, ionization energy from a neutral atom. Pretty good. Yeah, cool. Well, I was just wondering. So you did that.
So it has to be in a gaseous state.
Pardon me?
It has to be in a gaseous state.
Yes, yeah. Because when you say ionize, right? So
Oh.
therefore, yeah. Good thinking there. So what's the first ionization energy trend? It decreases down the group. And so it decreases down the group. So you see lithium, sodium, potassium, rubidium decreases down the group. You see helium, neon, argon, krypton, xenon, right? Decreases down the group. Other ways of looking at it. And quantum mechanically also predicts the ionization energy should go lower down the column. And so as we go down across the period, the effective nuclear charge should get larger across the period. So now, enough of those definitions, right? But let's see if we can fill up the electrons in the orbitals. So if we have beryllium, so Be is, what's the 4, right? So arrow up, arrow down, so 2, 4, right? So 1s. So we would write down 1s2 and then 2s2, right? And so those orbitals are there, but there are no electrons. How can you get electrons there? You can bombard it, right? Right, Vinny? You could bombard it with a neutron or something, and then we can get it, and then we can study the emission after that. So boron is 5. Nitrogen, so if you look at nitrogen, right? 2, 4, okay, 7. And oxygen also. And so that's how we go about filling the orbitals, where each electron has a different spin in the orbital, so they don't have the same quantum numbers. So the trend in the first ionization energy, to ionize beryllium, you must break up a full sublevel, which costs a lot of energy. So we hardly ever see ions such as Be+, actually, in our calculations. When we ionize boron, we get a full sublevel, which costs less energy because boron was 5, so B+. Some exceptions, nitrogen. To ionize nitrogen, we need to break up, which costs extra energy. So such a good thing. And oxygen, you need to have a half full sublevel, so also not too stable, right? You don't see much O plus also. So trends in successive energies, when we remove electrons, it costs more energy. And here's the trend. So as we remove more electrons, takes a lot more energy, so that's not really practical for us. So we'll just stay and focus our learning on the first ionization energy potentials. So now we go to the next concept of electron affinity. So what do you mean by electron affinity? What's the definition for that? What does electron affinity mean? It's defined as the exothermic or endothermic. So affinity, love for electrons, right? You want to draw electrons towards itself. The more energy that is released, the larger the electron affinity. So when energy is released, exothermic, and so the more negative the electron affinity, or EA. So we don't want to confuse electron affinity from electron negativity. That will be our other key word for this chapter. So what are our trends in electron affinity? Alkali metals decrease electron affinity down the column, but there are always exceptions to the rule. The highest electron affinity in any period, of course, are the halogens. And we see that a lot in our chemical reactions in the lab. And so if we take a look at electron affinities, right, here are the halogens. Look at their electron affinities. The halogen, so F, minus 328, minus 349, minus 325. So it has a lower potential energy, so it tends to draw electrons. Metals, we know, lose electrons, so they're oxidized. Non-metals gain electrons, they're the ones produced. So those are the words that we learned before in previous chapters, I think in chapter 4, right? So now we want to look at the metallic character of certain elements. We learned also this is chapter 2 or 3 or 4, that metals are malleable. You can pound them, you can pound aluminum to whatever shape you want it to be, so they're good conductors, and they're also easier to ionize. They decrease, metallic character decreases from left to right, so when you write down metallic character, so you want to put the arrow going from right to left. Right? And then metallic character, so now you want to increase this going down the column.
By metallic character, are you referring to its malleability?
Yeah, exactly. Malleability, being able to pound and form it.
Yeah, as far as how much resistance it has.
Exactly, yeah. That's a lot of fun, right?
Yeah.
Uh-huh. Yeah, so when they made utensils, right, spoons and forks with metals, and when they made silver also, instead of pure silver, they get some aluminum and just cover the aluminum with silver so that it looks like it's silver utensils instead of aluminum. So we know that metals also have high melting points, right? But the melting point decreases down the column. So the MP, the sum of the physical properties, melting point, the density, therefore, of course, increases down the column with the exception of potassium. But in general, the mass increase is greater than the volume increase. So here are some reactions of alkaline metals. Our last lab here at North normally deals with putting sodium in water and see how it starts to jump around and starts dissolving. And so this is exactly, and potassium also, we do that as one of our determining different types of periodic properties and physical properties of metals. For the halogens, the reactivity increases down the column, so they react with hydrogen to form the HX acids. So the melting point and boiling point increase down the column. And then the halogens, of course, so here's bromine. It's kind of like a reddish, orange, brownish gas, and chlorine, and of course iodine. And we should be able to write down their electron configuration. So for fluorine would be if you look at fluorine, so then you look at the noble gas before it is helium, so you have the helium as your core shell, and then 2s and 2p. So for fluorine, right? Fluorine has how many electrons? So 2s, 2p6, right? Or 5. And as you go down, you have 2s, 3s, 4s, 5s. And their atomic radius increases. Their electron affinity, right? Kilojoules per mole. Their melting point. So you could be asked what is the trend for the halogens. So this table might be a nice table to kind of have in mind. The atomic radius, the electron affinity, their boiling points, what happens to the trend, and what happens to their densities, it increases. So what's the reaction of alkali metals with the halogens? Alkali metals are oxidized while the halogens are reduced, and together they form ionic bond, exothermic, so that it gives off energy. And what type of reactions do we see? For example, we could see the electrolysis of water when we split water into hydrogen and OH minus, right? Or we can form ionic bonds, and when we put them in water, the reaction is quite exothermic and gives off heat. So any questions there? Next week we'll be working on chapter 9, right? And we actually did an experiment. Chapter 9 is set up in a different way. It's already posted online. And see how you respond to that, because that's actually a very, very important chapter also. The type of bonding, universal bonding. It was just posted. They just gave me the link this afternoon, and see how you like that, if you see it before or after. Somehow we lost chapter 7. They couldn't, either there was no removable card in when I got to the video, so we don't have. Yeah, chapter 7. You want me to retape it? We'll move on. So, for those that, let's see, are there any questions?
Just like the quizzes, are they already posted? Do we have any more for these chapters?
Pardon me?
The quizzes,
Yeah, the concept check are online also, right?
No, but the online quizzes, you're not going to do them anymore?
Because it's pretty hard, because to try to put it manually, ever since we switched to D2L. When it was Blackboard, I can do a quiz, like set up a quiz in 5 minutes. But when on D2L, it'll take me like 45 minutes to set up that 10 questions, because I have to manually load and type up and then put the values.
Miss, are those same quizzes, are they on the chemistry website that you published?
Oh, yeah, on that chemistry place, you can do that. And if you do that, email me your data and I'll give you some Yeah, so remember the chemistry place I told you
There
during
was,
first lecture?
What was it again, the website?
Yeah, so the website was, so when you type chemistry place, this used to be in my Broward. I used to have a link in Broward, so I typed chemistry place, and then let me demonstrate. I can find it here. So when you
Online dating sites or something?
chemistry place, I know, can you believe that? So we have to, yes. Oh my gosh, now it's really different, right? Because you have that link?
Is that it, the second one?
Yeah, I think
Yeah,
that
it should be a second.
Welcome to the chemistry.
Oh yeah, welcome to Chem Place. But it's not as bad now as when, say like in 2000, right? You type up certain words and just you see all the negative. Yeah. So then you click on the books available, right? Okay. Click on books available. Oh, somehow it's
you have to pay for it.
no, it's free,
Yeah.
and they're strong, right? And then, so if we go to chapter 8, so this is actually a nice place to go, and here are the self-quiz. So which of the following would be false?
So if we can email,
Yeah.
we can't email into D2L, so can we email those to your regular
Yes,
email?
yes. So actually, right. So as you go down here, and it says submit answers for grading, and it will ask you who to send it to, and then it will tell me that you did it, and I give you credit for it. Yeah.
But you can't email into D2L if you're
No.
outside of it.
Yeah, so it'll have to be my Cockroft at Broward. Yeah, so this is actually a good grade because these are just like questions from Troll, right? And I draw from the same test bank, and this is volume edition 1, whereas we are working on edition 2 and edition 3, right? The concept check questions I have on D2L are edition 2.
I mean, it also be the same question.
They're pretty much similar, right?
Yeah.
I don't know. I can't
Everything
remember.
will change.
But because the test bank, for every chapter, there are more than 200-300 type of questions. So, hence, chemistry is the type where you don't see the same questions again because they kind of random.
Well, no, they're all on Yahoo Answers. Check.
I know, exactly. It's really interesting when Chris mentioned that, people just typed that down, right? I guess a lot of students have already, because it's volume 1, first edition, have asked that question in About or Yahoo, and so you see these answers. Yeah.
I don't know what you're talking about.